Oh, so hi everyone. I'm really excited to be here and see everyone. Today my talk is about semantic segmentation and some related topics. And this is based on, most importantly, based on sharing of amazing Kaggle community, sharing solutions and approaches, also discussions in the open data science community, and my own Kaggle experience. And I'd like to especially thank Vladimir, Alexander, Selim, and Artur Kuzin for their inspiration and contribution. So first, just for a warm-up, can you raise your hand if you ever did a Kaggle competition? Okay, yeah, and another question, have you ever done semantic segmentation on Kaggle or outside of it? Okay, perfect. So we'll start from the basics, and if you have any questions, please, if anything is unclear, please interrupt me. And there will be also a short break in the middle for questions and a quiz. Okay, and so the focus is, after the basics, the focus is more on kind of simpler problems with, which arise in, for example, satellite imagery or medical imaging. So they are kind of simpler compared to real life scenes, understanding during like real life or self-driving. And also focuses less on architectures because you can read it in papers, and more on the overall pipeline, how you frame the task, and all external factors. Slides have links, and I'll upload them to Slack, so you can check resources there. Okay, so first, what is semantic segmentation? So if you have, for example, we are segmenting kittens, and we have an image of a kitten, we need to output a mask of the same size where we have identified which pixels belong to the kittens. So it can be seen as a binary classification task for every pixel of the input image. And so this was binary, and we can also do multi-class semantic segmentation. And in this case, we would be segmenting kittens, grass, trees, and sky. So this would be 4 different classes. So it's multi-class classification for each pixel. Another related task is object detection. In this case, we have 2 dogs and the cat here, and we want to predict a bounding box for each separate animal and assign a class to this bounding box. So there will be 2 boxes for dogs and 1 for cat. And so here is an important difference. Although the dogs are really close, but we know that these are 2 different dogs and not 1 huge dog. And so instance segmentation, so in instance segmentation, we also predict masks like in semantic segmentation, but unlike semantic segmentation, we separate 2 touching objects. So we have 2 dogs here, but although they are touching, we can see that they are different. So we need to predict different masks for different objects. So this is the difference. So to recap, we will be talking about semantic segmentation and a little bit about instance segmentation, but won't cover object detection much. And so why talk about semantic segmentation? One of the reasons is that, well, so Kaggle does a lot of competitions, but if you just take competitions for the last roughly 2 years, here are the competitions that involved semantic segmentation. So bolded competitions are where you had to predict some kind of a mask, and competitions in plain text are cases where you didn't have to do it, but still some winners or most winners use this approach to solve this problem. So this is a sizable chunk, and it's an important problem. And it's also really useful in practice. So some examples. This is the image that Mikhail already showed. So this was Carvana image masking challenge, a binary classification task. So the task is clear, but why it's useful? Well, it's useful because they can take a photo of the car in the studio, and then if they have this mask, they can remove the background and put this car image into any background they want, for example, white or any other. And here, a curious fact is that the winners were separated by just a few pixels per mask. So computer vision can solve this task really well, much better than humans can. Another example was the STL satellite imagery competition, where the input was satellite images in different bands, both RGB and several infrared channels. And the goal was to predict basically a map. So it was a 10-class semantic segmentation problem. Another one is a recent, again, you've seen this picture, a recent data science ball where the goal was to segment instances or segment cells into different instances and predict masks. So it's instance segmentation. And one more example of instance segmentation is an ongoing competition for workshop on autonomous driving on CVPR. So this is an example of more complex scene, which is harder to solve. And an example where you didn't have to do semantic segmentation, but it was still useful. So the stellar sea lion population count, you had 5 different types of sea lions, and you had huge images of them taken from a drone, and you had to predict the count of different kinds of sea lions. So you could solve this as a regression problem, but it was, you had the coordinates of individual animals, so you could also frame it as semantic segmentation, and this helped to understand what the model is doing, to see where it's making mistakes, and so it was also a viable approach. And yeah, there are also a lot of competitions outside of Kaggle, most notably SpaceNet, which is again about satellite imagery, but also a lot of others. And so notable data sets. So if you read papers about semantic segmentation, you're likely to see Pascal and Coco data sets, and also self-driving, driving data sets are also popular, like cityscapes or mapillary vistas, and there are a lot of aerial and satellite imagery data sets, and not that many good medical data sets. And so in practice, if you already have a semantic segmentation task, that's great, okay, but often you can, as we've seen, you can solve it, you can have some different tasks, but semantic segmentation can be a useful intermediate step. Why? So first, it's really simple to implement. It's just slightly more complicated than doing simple image classification. And second, it can allow you to see what the model is doing. Also, it doesn't need that much data to train, because the target you are predicting is really high dimensional. So if you're doing image classification, then the target is just the class. But if you're doing semantic segmentation, then the target is the whole image. So it's a lot more information for the network. And labeling is relatively easy, so you could do it even in Paint, for example. So yeah, in practice, it's also quite useful. Okay, so first, UNet. This is a classical architecture, and it was used, and it is still used a lot. So it is a really, really solid baseline. It's easy to implement, and it almost always works. So it is like, I don't know, if you're doing image classification, you often start with ResNet. If you're doing semantic segmentation, UNet is a perfect baseline. And we'll see how it works. So how many people have seen this image before? Okay, a lot of you. So we won't, let's study what happens here in detail, and then we'll have time for questions about specifically this part. So first thing is, like, our input is on the left. So here we have an input. In this case, it had just 1 channel, but it can have 3 channels or more. And the output is on the far right. And so what happens is this, like, first we're doing convolutions and ReLU nonlinearities, so like you do for image classification. And if we follow, then you do max pooling. So if you follow that path, this is called the encoder. And this encoder is really similar to plain VGG thing, that VGG architecture, which can be used for image classification. So in the end, here we have some features about the whole image. And this is great, but we want to do really precise segmentation of each individual pixel. So if we just use these features, then we won't have this precise information about what is, which pixel belongs to which class. So then we have the decoder, which starts from here and goes up to the output. And so this decoder needs to upsample the input to the resolution of the original image. And so for upsampling original, you net use transposed convolution, but you can also do simple nearest upsampling. And again, you have convolutions and ReLUs and so on and so on. But we also, an important part of UNet, so what makes UNet a UNet, are these gray lines, which are skip connections. So these skip connections, they, for example, the topmost line, it takes features after the second convolution, so 64 channels, and it just passes them through, and then we concatenate these features with the features which come from the decoder. So we had 64 channels from the inputs, from the encoder. We had 64 channels coming from the decoder. Then we concatenate them together. So we have 128 features, and then we pass them through the convolutions and get the output. And so output has the same width and height as the input. And if we're doing binary segmentation, it can have 1 or 2 channels. And if you have multi-class, it has the same number of channels as the number of classes. And so in each pixel is a probability, and then we need to threshold it at some value to get the final mask. So I want to stop here and make sure that, so if anyone has a question about how this works, please ask it now. Yes? Yeah, that's a good point. Yeah, so in this case, the output has different size as the input. And in the original UNet paper, so what happens is that first they take a crop here, and then also I think they're using, so when you're doing convolutions, you can do different kinds of paddings are possible. And if you do not do any padding at all, then the output size after convolution is smaller. So this is what they were doing here. And this is why the output has different size. But nowadays, so if you just want to use UNet as a simple baseline, you would do instead valid padding, which makes sure that the input and output has the same size. And you also don't do these crops. So yeah, in the original paper they did this, but it's more convenient if the input and output have the same size, and it's easy to make sure that they are. Yeah? Yeah, I will cover that like at the end, okay? Yeah, but in general, it's nothing crazy is needed. Okay, so yeah, I will continue. If there will be any questions, please, yeah, stop me at any time. Okay, so the basic building blocks, as we said, the convolution ReLU, which gives us VGG-like encoder, and yeah, as I said, that it's common to not do any extra cropping and use valid padding everywhere. This way, the size remains the same. And yeah, you can also add batch normalization. You can use pre-trained networks, and yeah, we'll talk about these details in a minute. Okay, so an important point is that this architecture can be applied to any image size. So if you have input of, like when you're doing classification, usually you convert each image to the same size, like 224 or 300 by 300. But when doing semantic segmentation, usually you don't do that. So because this network can be applied to any size, because all operations either don't change your input size, or they do like 2x downsampling, and you can do 2x downsampling for anything, or upsampling you can also do for anything. So there are only two caveats. First is that your data must still fit in GPU memory. So if the image is too large, then it won't work. But usually the size that can fit is quite large. So for most common architectures, at least 1,000 by 1,000 pixels can fit during inference. And second point is that so if the input size is not a multiple of number of downsamplings and upsamplings, then you'll have issues with not matching sizes. So it's easier to pad to this multiple, like to 16 or to 32, depending on the architecture. So this is, I think, the most important bit of the talk, is like the typical pipeline, because it's different from what you do for classification. So what you do, you have two separate steps for training and for inference. So for training, usually you do some fixed sized crops. So you have a large input image and you take crops out of it, just make square regions out of this image. You, again, apply augmentations like you do normally for image tasks. You arrange this in batches. And you can do a lot of hacking in how you select these crops and how you prepare them. And so you train on some one size, say it's 256. And then during inference, you use a different size. So during inference, you either try to load the whole image and pass the whole image, even if it's large, through the network. And if it doesn't fit in memory, then you use large batches and do stitching, so stitch these batches together. So why do you do this? Because, well, on the borders of the image, the quality is usually worse because the network has less context. So it's better to have, to not have any borders or have minimal amount of borders and stitching. So this is how it looks like. So this is an image from, I think, Toronto aerial image dataset. So let's say the goal is to segment roads and buildings. So as you can see, there are like crops of the same size. And so why same size? We could do like some crops would be larger and we would rescale them to the same size. But in this particular data set, it would be not ideal because all roads are roughly of the same size and buildings are roughly of the same size. So you don't want to change that. You don't want to make the job of the network harder. And so here, another interesting point is that, as you can see, there are more crops near buildings and roads than in the forest. So this is also useful if you have like some areas which are easy for the network. It's easy to see that this is forest, there are no roads here, but you really want to be precise about how you segment roads and buildings. So in the data generator that we write, we can make more samples in the interesting bits of the image and less samples where the network is confident in its prediction. So this can influence the solution and speed of convergence a lot. Another interesting bit, so this is quiz time. So another interesting bit that we could rotate these crops. So we have a crop, and here the crops are all like aligned with X and Y axis, but instead we could take a rotated crop and feed this into the network. So it's easy to do, and this is the same thing as rotation augmentation that you can do for image classification. And it's great because it increases the data size, but in this particular case, it might be not great. So the question is, why? So I think this is a hard question unless you know the answer, but maybe you have some ideas. Sorry? Yeah. So this is one reason, but there are multiple answers to that. So one reason is that images are oriented to the north. So north is upwards always. So although it's a map and we can rotate it anyway, but here north is up, and in fact in many areas most roads are oriented in the same way And so if we are trying to build a generalizable algorithm, then we should always rotate. But if we are on Kaggle and we want to make the best score for this particular data set, then we can exploit this, that yes, roads and houses are often aligned to the also image size. So maybe now you'll have some other ideas why it can, yes? Yes. Yeah, that's right. So in fact, in the DSTL competitions, there were different classes, and for some classes, even though there were no preferable alignment, still it was really important to not apply rotation. So this is another reason. Any ideas? Yes, shadows. So again, so this is the fact that most satellite images are taken in the same time of the day. This is due how well satellite mechanics works. And the shadows are, if it's sunny, so the shadows are pointing in the same direction. And so if we rotate, then the shadows will be pointing in some strange, unusual direction, and the network will, again, the network's job will be harder. Yeah, so, yes? Yeah, that's a great point. Yeah. Yeah, so that's a great point. So to repeat that, when we're doing the augmentations, we need to transform the target as well. And if the objects are small or if they are very thin, then this rotation can make the target look worse for the network, and this can be an issue. And also for really small objects, when we do rotation, even the input can become of less quality. Because if there are like an object of 5 pixels, say some bicycle, and we rotate that and all these pixels are messed up. So this is another thing that can make a difference. So to sum up, that augmentations, as always, should be selected based on the task, and there are a lot of specifics in medical and satellite imagery that you need to take into account. And yeah, you can just try different things. So try with this and without this augmentation. Even if you don't understand the reason, but see that this augmentation hurts, don't use it. Okay, next. So this is an example where we can actually use different scales. So rivers look roughly the same depending on the resolution. So what we can do is we can take crops of different sizes, and then we resize them to the same crop size which is used during training. And so these images are both rivers, and it's like clear how to segment them. So in this case, such approach for crop generation can be useful. And okay, so inference, if we have a very large image, then we have to do stitching, and usually we want to do it with some overlap because predictions on the borders are less good, and if we have more compute budget, we can do more overlap. And yeah, if we can fit it in memory, then we can just pad, like zero pad, or do some reflection padding depending on the data set, and do inference on full images. Okay. Now some details, some implementation details. So when you're doing training, there can be issues that GPU is not a bottleneck, and especially in image segmentation, you have to be careful with how you implement the data generator, because if the images are big, then either input-output can be a bottleneck, so then you try to load it all in memory, or try to use an SSD if you don't already use it. Then also decoding can become a bottleneck, so you profile your code, you use faster libraries, you use more workers. So yeah, it can be challenging to make sure your pipeline is efficient. And for inference as well, so if you need to predict a lot of images, then often GPU is not your bottleneck, so you need to do a lot of encoding, decoding. Also, images are really large, especially if they are not compressed. So you try to compress your predictions, and there are various tricks. Like first you can create masks and compress them. They compress really well. But also, if you need probabilities for ensembling, for example, then you can binarize these probabilities, because again, in a lot of cases, the probability is some low number, and you don't care which it is exactly. So essentially, you like quantize your input and also compress it, and also you try. Yes. Yes. So yeah, two options are, first you can binarize it like below some threshold and above some threshold, and this is fine if you only need this, but often you need to have some probability. For example, you need to average several predictions, or you need to do some like second level. In this case, a simple hack is for example, the probability is from 1 to 0, you multiply it by 100, you have numbers from 0 to 100, and then you compress this NumPy array. And usually it compresses really well, because there are a lot of areas there where this probability is the same, like close to 0 or close to 1. So this allows you to save space, because otherwise you would it won't fit if the data set is very large. Okay. Now, so we've seen how the pipeline works, but there are a lot of knobs to turn. And so as Michael said in the previous talk, so he outlined the things that you need to think about, and these are like basically important things specific to semantic segmentation that you need to think about. So let's start with loss. So I think this is like the most important thing, and Michael already covered some examples. So first, again, at the end of the network, you have an activation and two, like if you are doing just predicting the class, there are two choices, sigmoid or softmax. So softmax is used if you have just one of several classes, and sigmoid is used when you have a binary classification task, or if the classes are not mutually exclusive. But actually, you can also use sigmoid for even if you have multiple classes. So here, I don't have any good rule of thumb. So try both, even if it's multi-class. In some cases, sigmoid can work well. And then, so this is the output activation, and then the loss. So cross entropy is the standard loss, but it has several problems, and so often it is used in combination with dice. And there are also some custom losses specifically designed for semantic segmentation tasks, but I don't have much experience with them. So dice in more detail. So dice and Jacquard are like metrics that can show us the quality of the semantic segmentation. So Jacquard is basically area of the intersection divided by the area of the union, and dice is, well, really similar, but a bit different. And so why use them as losses? Because usually this is the metrics that we care about. So Jacquard or intersection over union is just often the target metric that we optimize on the leaderboard. And even if it's not the target metric, still it's much more useful than, for example, per pixel accuracy. So per pixel accuracy is completely useless metric for semantic segmentation. And this is why doing just cross entropy is often suboptimal. So how do we, but these things are not differentiable, so we make them differentiable. Let's go here. So this is like soft dice, a differentiable version of the dice, and this is an example. So intersection, instead of doing an AND, we do multiplication. So input is 1 or 0, and target is probability from 1 to 0. So if it's high, then intersection is high. Again, union uses the same idea. We take, so input is 1 or 0, that's fine, and target, we sum it. And so the higher the probability, the higher the intersection, and then we do just calculation and invert it because we want the loss to be low, and like good dice is high, so we need to put minus here. And so compared to cross entropy, dice allows us to work with class imbalance better because dice is global. So if we have some small object, then and we mispredict it, then a little, then cross entropy will not care much, but dice will care a lot because intersection and union change a lot even if the object is small. But the problem is dice that it forces the network to make confident prediction, and this is bad if you do averaging in the ensemble or if you want to see which examples are hard for the network. So that's why usually people combine dice and cross entropy. So you take a weighted average of both losses, so the network tries both to predict something softer and also tries to make confident predictions. So this usually works best, and the weights are a hyperparameter which you tune like everything else. Okay, then another thing is that you have a lot of inputs, in a lot of freedom in how you design the target. So the target can be just the classes that you need to predict, but you also can include additional things. One example not covered here, so because due to the question with small objects, so small objects are hard anyway. For example, if you try to predict fences on the satellite imagery, it's really hard because they are just a few pixels wide, and an easy hack to improve this is to make target larger. So you can do, using computer vision algorithms, you can make fences artificially larger, and the network has more information about them, and then it predicts the mask, and you shrink the mask again. So this improves results. And another thing, so first is Michael already covered it, so we want the network to be good at separating cells. So we ask it to predict not only the cells themselves, but also the borders between them. So we add an extra class, which was not in our task, and we don't need to predict it, but using these predictions, we can improve segmentation. And again, we can create the target using simple computer vision techniques. Another example from the same DSBO competition, we can, to help with segmentation, we can try to predict the vector field, which is pointing to the center of the cell. And an interesting thing about this vector field is if you're doing rotation, then you need to rotate the vectors, so it's different from rotating the masks. And yeah, it was used by the 4th place team there. So here are their examples. Another thing, okay, maybe we'll skip this. Okay, so now about training. So in general, there are no significant differences from classification. The problem is that you usually cannot make the batch size be large because these segmentation networks, they require more memory compared to classification networks, because you have, first you sometimes have larger crops, and then you also have more gradients because you also have the decoder, and the size of the features is large in the decoder too. So to recap, usually you are constrained by the batch size, so you just take the largest batch size you can afford, and 4 or 8 is already mostly good enough. Also, as we said, yes, sampling is important, and Adam Optimizer is a good baseline, so you most likely be fine with it and won't notice a significant difference. And yeah, also overfitting is less of an issue because you have a lot of signal and in the target, and the network really doesn't overfit that much. So often most often you are underfitting and need to create some to try to find a better encoder architecture. Okay, an interesting question is the crop size. So as we said, we're using fixed size crops. And for example, if the crop size, but which crop size do we choose? There is a thing, so receptive field, This is, for example, if we have convolution, 3 by 3 convolution, then everything outside of these 3 pixels does not influence the result in this pixel. If we stack convolutions, we increase this receptive field, and also we have downsamplings, which increase the receptive field even more. But even then, so if we take the classical UNet network and we try to calculate receptive field, this is the first link, has code for it, because it's like, it's easy, but the math is tedious. So if you calculate it, it's 140. So it's not that large. Often we are using, and there is not much point in using a cropped size during training, which is much larger than that. But even this is only theoretical receptive field. In practice, the effective receptive field, which the network has, is smaller. So these are images from a paper, and this which try to analyze this, and this black rectangle is theoretical receptive field, and the white thing in the center is like the actual receptive field in practice, which you observe in practice. So what does it mean? If we have some image and we want the class of this pixel depend on some overall scene context, then this receptive field helps us to do this. But if the class of the pixel must depend on a pixel really far apart, then we have a problem. So we have to solve it either with a deeper network or with downsampling of initial data. So that's a tricky thing. Okay, I think we've mostly covered augmentations. The only thing I want to mention, like provide some links for implementations, and said that, again, watch out for CPU usage during augmentations. They can really slow you down. Okay, so encoder is probably the most important bit of the architecture here. So this is the thing that prepares the features. And some popular choices, so VGG is a classical UNet, and also ResNet. ResNet, for example, 34 is really popular and well-performing. And well, also basically any architecture from image classification, you can use it as an encoder for the UNet-like network. And yeah, for example, the DS Bowl winners used really deep networks despite the small size of the data and relatively like simple data, but still they found out that really large decoders or really large encoders are needed here. And so an interesting trick is that if you are using a large encoder, then especially on large crops, and this will take a lot of memory, this will slow you down, and this will not allow you to have a large batch size. So there is a trick to make it work better. It is to insert some extra downsampling operations into an existing encoder, and this way the size of the features will be smaller and you'll use less memory and it will perform faster. So it can be really important. So for example, you can insert it after the first few convolutions or even right at the start. And so importance of pre-training. So pre-training is a must for doing classification because it's like very simple and gives great results. For semantic segmentation, it's less clear, but still in a lot of cases it is beneficial. So here's there's a link for implementation example with pre-trained VGG and ResNet 34 in PyTorch. And this shows that pre-trained network on either ImageNet or another segmentation task can perform much better than a network trained from scratch. But still, in a lot of cases, training from scratch works good. So, and you can pre-train on ImageNet, or you can even pre-train on synthetic data. So this is a link for Keras UNet pre-trained on synthetic data shown on the right. It also works well, so it's an interesting topic. And also, if you have more channels, so if you have not 3 channels, but for example, 10 channels coming from satellite imagery, then it's not trivial to use pre-trained network on ImageNet, but still there are ways around it. So you can either randomly initialize the first convolution, but copy RGB weights, or you can also duplicate this channel. So this is slightly tricky, but yeah, you can still use pre-trained networks even if you have more channels. Okay, I think we'll skip the decoder. Most important thing is that like upsampling with just nearest upsampling works good enough, and it's easier to tune than transposed convolutions, but there are also a lot of interesting things there, and we didn't really, so there are a lot of architecture questions that I don't cover here. Please see papers. Okay. And how much time do I have? Okay, so about instance segmentation. So we see that this network it can be naturally applied to semantic segmentation, but to do instance segmentation, we need to somehow separate separate instances. So the easiest way to do this is to just find non-overlapping instances. But if the instances are touching, this doesn't work well. So another also simple approach is watershed, different variants of watershed transform. So this is how it looks. This link has a really intuitive explanation of it. So you can turn a mask. Imagine that a mask is a kind of a mountain surface with valleys and like ridges. And the idea of the watershed is that you flood this this landscape with water, and you have ridges which separate different areas. And the idea of so this is the watershed with like marker-controlled watershed. So we have initial seeds. So you know that you have 3 instances, and then you want to separate the mask into 3 different instances. And so you can give these seeds to the watershed, and it will separate the rest by flooding starting from these points. So how do you get the seed instances? For example, the easiest way is to use a higher threshold. So if you're predicting masks and you have 0.5 threshold, then you can, for example, for seeds, you can have 0.9 threshold. Usually it's high. The probability is higher, closer to the center. Another way is you can create an extra target and either create a target for centers or create a target for borders and subtract borders from centers. Okay, and another interesting thing is second level models. So I think I'll just cover it really briefly. So the idea of the second level model is that you can so you predicted some mask and maybe some other layers, and then you can create features from this mask. So for example, a simple feature is just sum of the intensities. Another feature is different topological properties. For example, if you are predicting houses, you know that the house is roughly rectangular and it should not have some weird, like this looking wired-looking shape. So you can create a topological features from the mask and then choose the threshold for each building individually that gives the shape which is most similar to a building. And another example is if your final task is not segmentation, but for example, regression, then your second level model can be doing this regression using features you created during semantic segmentation. Yeah, I think we'll need to skip this examples. So it was second level model were used in DS-ball solution and in stellar population count because the task was regression. Okay, so another thing is that if you're doing, if you want to do instance segmentation, then another approach is to use just mask RCNN, which is a ready-made network that already natively supports instance segmentation because it first predicts the bounding boxes and then does semantic segmentation inside each bounding box. So this works great, and it has a nice Keras and TensorFlow implementation, but the problem is that if you need to hack this model, it can be much harder because the implementation is much more complicated than UNet. So you can code UNet from scratch easily if you can code classification solution. But to implement Marscar CNN, you cannot just simply implement it from scratch because it has a lot of components, a lot of details, and if you want to modify it, it can be harder. But if you have just instance segmentation, then it's fine. Yeah, so there's no silver bullet, and so if the task doesn't involve, does not require you to do semantic segmentation, then you can just optimize the target metric, like do regression or classification directly. So it really depends on the task. And so I think the main takeaways that you know how the general pipeline works, and that you know important things to tune and how they influence the final result. And also learn to see where semantic segmentation can be applied, even if you are not required to use it directly, because it sometimes works surprisingly well. Okay, so this is all. Thank you very much for listening. Okay. Questions? Okay, yeah, I hope we can. Yeah, there's a mic.
I have a more general question. Did you do anything with CNNs with respect to music?
With music?
Yes.
No, I did not. So I know that there was a recent competition on speech recognition, and CNNs were used there, both two-dimensional to analyze histograms and one-dimensional to analyze the wave form directly. But I personally didn't take part of it and didn't do anything with sound and convolution networks, sorry.
Okay, then take it.
Yeah, and by the way, so there was a question at the start about computational resources required. So they are not huge. So, but yeah, you need memory. But in general, these networks are much faster to train compared to, for example, Marscar CNN or faster CNN. So they are. Because you can take a really shallow encoder and still get reasonably good results. So not a lot of resources required compared to other networks. Yeah, sorry, is the question?
Hello, hello. It is a microphone. Okay, interesting. Yes, my question is pre-processing. Do you do any pre-processing? Does that help? Or do you just rely completely on the network?
Yeah, pre-processing is really important. So first thing is that if you're using pre-trained network, then you must do the same kind of pre-processing which was used for training the network itself, the pre-trained network, so standard ImageNet pre-processing. Also, so for example, for satellite imagery specifically, there are things called indices, which are combinations of different channels involving infrared, which can reveal important information. And although the network in theory is able to build these things, but in practice, any help we can do for the network is good. And another interesting thing is, so for example, in this data science ball competition, there were not a lot of data, and images, there were two kinds of images. There were images with black background and white cells, and images with white background and black cells. And obviously, well, all teams they inverted either images with black background or images with white background so that images look similar to each other. So this is, again, in theory, network can learn both, but in practice, it's better to help it. But an interesting thing is, so how do you think, which works best, inverting, having black background or white background? Yeah, so if the network is really small and you're training it from scratch, then having black background is better because So if you do preprocessing, if you don't do preprocessing and have 0 as black background and 1 as 1, then at the end, the network needs to output 1 for cells and 0 for background. So the network, it's easier for the network to learn identity function than to invert your, so even such details in preprocessing can matter. I think no. So I think it depends on the activation function, yes. So this was with ReLU activations. Yeah, I think it does depend, yes. So this is more like a curious detail because in practice you will likely be using a pre-trained network, and there this, like the way you invert does not really matter because there it's not learning identity function anyway, but yeah, that's still preprocessing can be important.
Yes. Hi, Konstantin. Regarding post-processing, it is possible to use k-nearest neighbors or erosion and dilation or something related to the problem like the average of the cells. This cell is too big, so I'm going to split it in 3 times.
Yeah.
No.
Yeah. So yeah, a lot of options. Yeah, for post-processing, and post-processing can be also really important. And yeah, so I don't know what to add extra. So you described that nicely.
Thank you so much.
Thank you for your presentations.
Thank you. Thank you, everyone.
Yes.